Hello and welcome to the lecture on texture mapping within the series on computer graphics course at KAUST. Today we will be talking about texture mapping, which is a technique which enhances the visibility of a certain detail and increases the realism of the scenes. As you can appreciate, the world around us is not consisting of solid structures which have just one color and have no other features. Often we can see that certain structures are rougher, and we can see this roughness in some form. We can see walls that they have certain small structures from the material they are built from, or they have even the composite material, which are then manifest itself by some variation in colors. And it's not only the color itself, which is being reflected from the surface, but it's also the different reflection qualities. So some structures can be more specular, some structures can be more matte, more diffuse, and they are mixed within one composite material. We have also some other structures. For example, some little imprecisions, like for example, if we look at our skin, we see that there are some wrinkles. We can see in the fabric. If we look at the fabric closer, we see that there is some structure which is demonstrating the art of creation of that particular fabric, the individual structure of the thread. We can see that wood has, for example, grains and so on. So, and all this, in principle, could be represented geometrically. So we will have a geometry in a composite material where there will be different geometries and with different optical properties assigned to each of these elements. But this will result in often in an infeasible scene, because the scene will become suddenly much more complex than if we will be representing the scene even more with a more solid representation. Therefore, the computer graphics has developed a technique of texturing which allows us to add some detail to objects, which is more represented in an image, and it's sort of placed on that structure. As if you would be placing a wallpaper on your walls, in the same way, which is a piece of paper, maybe a roll which is having a recurrent pattern. This is a physical process of texturing. And we will be performing something similar, adding the structure, making the objects looking more interesting and more naturally appearing. If you would then, however, have a closer look, very, very close to the surface, you might sometimes realize that the structure is geometrically not there, that it is just a representation of an image. But typically, these scenarios will be highly unlikely. In the given scenario of, for example, computer game, the player will not have a chance to inspect a particular material because he or she will be occupied by reaching the goal of that particular game. So you can think of that everything can be somehow wrapped with this texture pattern. And the question is, first of all, we need to get a particular textures. So the question is how to get those. And the second question is, how do we put these textures, how do we wrap these textures onto the particular objects? So the origin of a texture can be coming from various directions. It can be painted by an artist for the purposes of creating the texture. Maybe it can be already directly painted in the 3D scene on the 3D objects, but it will then sort of unfold itself onto an image, which can be then possibly also reused or stored as a texture for later use. Another way could be to acquire such textures from the real world. So if we want to have a concrete material representation, perhaps it would be a good idea to take some pictures of a concrete and create a texture out of such photographs. A third way could be that such a texture is being generated by some kind of procedure, so that we have a simulation, physical simulation, that generates us a certain visual appearance on a computer, and then we capture this appearance in the form of an image. This image can be typically a two-dimensional. If we are talking about textures in computer graphics, if we do not mean add any other adjective, it would mean two-dimensional textures. But there are also three-dimensional textures, which are, you don't think they're of wrapping the texture around an object, but rather carving the object out of this 3D texture. So imagine that you have a block of a particular material, and you will be sculpting out of this material your object. So this would be the 3D texturing principle. In this lecture, however, we will be focusing more on the 2D texture mapping. The second problem is related to, if we already have a particular texture, how do we place it on our object? Which is not a trivial task, because this texturing must adhere to certain desired properties, and it should be placed such that the texture aligns with the geometrical features well and is of good quality and doesn't change somehow its appearance or the appearance of the underlying geometry. Typically, if we are having our scene represented with solid objects, we would, for example, in ray casting, ray tracing, we would be fetching a particular surface position which a ray is intersecting, and at this position we would be fetching the information about the various geometric properties, such as the normal, for example, but also the reflectance of our material. So this would be the color and the various color or material properties of this particular object. But these values, the reflectance color and the material properties, will be constant for the entire object. The surface normal will, of course, vary. But here, in case of texturing, we will have this texture wrapped over our object, which will mean that for each surface position, in addition to the material properties or the color, we will also have a unique color which comes from this texture. We would need to find out which color that is. And for this, we are using a operation over so-called texture fetch or a texture lookup. So at the position on the surface, we need to find out what are the values of the pixel, and this value of the pixel is found in the texture image by two parameters for the two-dimensional case of a texture, the UV coordinates within the texture. The image, texture image, will be normally parameterized, although it might be of various resolutions, but the parameters U and V will be typically running between 0 and 1. And although they might extend this range, and we will be talking about that later. But we would need, in order to find out which color from the texture is being mapped to particular surface of our 3D geometry, we would need to use these UV coordinates for performing the texture lookup. This operation of a texture lookup or a texture fetch will return the color of the texel, as it is called in the texture space. We can perform this color lookup with a operation which we are already familiar with. We will be using our U and V coordinates running between 0 and 1, and we will be multiplying them with the resolution of our texture. So this will be the resolution of our texture, and of course we will be offsetting it by 0.5 within our texture size to reach the center of our pixels. And then we will be rounding the information so that we reach actual value of a particular pixel, and that will be the coordinates of the pixels for our texture image. The texture fetching will undergo a certain transformation, therefore, formally from the positions in the 3D space to a position in the texture, and in our case, two-dimensional texture, and the coordinates within this texture space. So this is one transform, and this transform will be sometimes quite similar to a viewing transformation, which we already know about. And this, we can see that the viewing transformation is somehow also linked in computer graphics. So for a particular position on a surface, we would like to know where it is located, this surface point in our image space, or the other way around. If we want to perform certain picking, we would like to know what pixel is then corresponding to which surface position, and for that we will perform the inverse viewing transformation. So you can see these two transformations rather similar because they both do transform between 3D space position onto an image position. And we will therefore use a lot of machinery which we already know also for the texture mapping purpose. Let's warm up with a very simple approach for a texture mapping. Imagine that we have an image of a wooden floor, and this wooden floor is nicely aligned with the coordinate system. So let's say that we will have here maybe an X, and here will be a Y coordinate, and we would like to now place a texture of this wooden floor on our planar object, planar geometry. Well, the simplest mapping could be that, of course, our wooden floor will be of a certain resolution, maybe 1K times 1K, and therefore which would be then, of course, mapped to 0, 1 coordinates, and we would like to somehow now map between the actual positions in the 3D space. So here will be 0, maybe here will be, I don't know, 1 meter, 2 meter, it will be 1 meter, 2 meters, and so on. We would like to perform a transformation between this between the positions in the 3D space into a position in the texture. And for that, we will just use some multipliers that will turn our x and y values into the range 0 to 1. This is a very simple example, and it is quite limited application of texture mapping. It would only work for planar surfaces, although there are rather many scenes in which the surfaces will be planar, like walls and floors and ceilings, but not all objects are of planar structures, which we would like to texture and add some visual detail to it. This example also indicates that it will only work if we will be aligned with the coordinate system, which is clearly not often the case. So our houses and the architectural details there will not be always nicely aligned with our coordinate system. Also, we need to take into account the possibilities of misbehavior of our texturing process. We have learned in the signal processing that if we are taking some samples from one sampled representation and placing them and resampling this sampled representation, we can experience certain artifacts. So, for example, if we will be performing texture fetching, as I described it to you in the way that we are just fetching the individual samples and rounding them up, we will end up in something like this, which is a nearest neighbor interpolation or nearest neighbor resampling. We can see that in the front, we have here quite some staircase artifacts because the different positions on our plane are fetching the same texel. And there is no interpolation between the neighboring texels, which will smoothen it out. Even worse, what is happening under this grazing angle in the background is that this texture fetching becomes more of a random process. And the more far away we are, the more random it becomes which exact pixel or texel is being fetched. And the more necessity of a certain filtering becomes apparent. While such a texture appearance such horrible texture appearance will appear only under such grazing angles. However, for a static scene, if we will have a dynamic scene, so the camera will be moving or the object will be moving, all these random appearances of our texture fetch will result into popping artifacts, and they will be changing dramatically and will focus our attention only in this area. Therefore, we will not be able to enjoy the rest of the scene because our eyes will be dragged to this salt and pepper type of noise which will be happening in the background. Therefore, in the texturing, we will be also needing to apply the theoretical concepts and the signal processing machinery in order to filter the textures so that the appearance will become visually pleasing. To map from the surface position into the texture, we employ either the texture coordinate functions or we somehow pre-compute this texture coordinate mapping. There are various functions which can be used, and they have already been used before the computer graphics. So a typical example would be in cartography, where the cartographers were coming up with various ways how the spherical appearance of the Earth can be mapped onto a 2D map. And there are various mappings, many dozens of mappings of sphere to plane that have various qualities. Some are trying to preserve areas, or at least areas where the continents are. Some are oriented on preservation of angles, while the area or the distances will be less of an importance. And other mappings are focusing on distances. Some are also interested in just keeping and preserving the structures in their close to their original appearance on the sphere for regions which are inhabitable. So, for example, we could see that areas such as Greenland or Antarctica would be maybe much larger in some mappings than the continents really are as compared to other continents. These texture coordinate functions are sometimes called surface parametrization, or typically in the jargon of computer graphics, that will be also called the UV mapping, because we are eventually after the values of the U and V parameters in order to be able to perform the texture fetch. These texture coordinate functions will need to have various properties from case to case, but often these following properties are necessary that they fulfill. One property would be bijectivity. This means that we would like to have a unique one-to-one mapping between the position in the 3D space and the position in the texture. This means that, for example, if we will be mapping a texture map of Earth or other planets on a sphere or approximately sphere object, we don't want that, for example, New Zealand will be appearing twice in that map. That would not be a good map of Earth if there will be one island represented twice. There are other scenarios where this is, however, not the restriction and a repetition is indeed desired. Imagine that you would just like to represent a bricked wall by the texture of bricks. For that, the bijectivity would not be a criterion. Actually, the opposite will be the case. You would like to repeat this small texture and reuse the memory stored for the texture many, many times because of the monotonicity of the structure you would like to represent. But other property, for example, is size distortion. So you do not want to change the size of the mapped texture within your scene. Imagine that you have these bricks, as we have mentioned them, and you would like to have the brick sizes approximately of the same size when mapped on a particular geometry. This mapping should not be changing that on one end of the wall the bricks will be half the size than on the other end. That would be a bad texture coordinate function which will result into such an artifact. Also, not only uniform scaling, but also non-uniform scaling should be avoided, like shape distortion. Imagine that your texture contains circles, and these circles should be mapped as circles onto the 3D geometry, but at some point they will be stretched and they will be forming ellipses or other weird shapes. So this is something what the texture coordinate function will be not doing very good job if our shapes encoded in the texture will be sort of distorted based on different placement on our objects. And also, we should have a texture mapping which would have possibly as few seams as possible. So if you are imagine that you have a texture, a paper which you want to wrap around a closed object, then necessarily there will be some seam. You need to somehow open up these wrappings in order to perform this mapping. But hopefully these seams will not be too apparent, or there would be not too many, just as many as necessary. As we know, in computer graphics, we can have various representations of our objects. We can have, for example, a representation which is an implicit or a parametric, coming from the calculus or mathematical descriptions of these surfaces. It can be a discretized representation of the surface approximated by a set of triangles, for example, as well. And for the parametric surfaces, the um, advantage is that parametric surfaces are parameterized by two parameters, and they typically run between 0 and 1 in order to define the particular surface. So, for example, a sphere could be represented by a parametric surface, and using three different parameters, we can, or one constant parameter, which would be the radius, and then the two parameters for the angles would be the parameters for that particular sphere surface. But we can have also other representations, like implicit representations. However, for those, it is not very clear which texture parameterization we can use. That's the advantage here for the parametric surfaces, because their parameterization of their surface gives us a direct mapping to the parameterization of the actual texture image. So the UV can serve both for parameterization of the surface and as well for the parameterization of the corresponding texture image. The texture would not naturally would need to be corresponding, so that the features which are on the surface will be nicely matched with the features which are in the texture. For implicit representations and triangle meshes, we will need to have some other solutions. For triangle meshes, in particular, the solution is that at each vertex where we have its position and color stored, we will also be storing the texture coordinates, which will be pre-computed through some other process. So let's have a look at what type of parameterization we can use. And this parameterization, we can also see that can be sort of taken over. So we first parameterize an object based on some proxy object, then we get the texture coordinates, for example, and store them at the triangle vertices. That is, for example, a possibility. Let's have a look at some parameterization functions which define us the mapping from the surface to the texture coordinates. One such a parameterization function could be a planar projection, meaning that we have here a nice texture, which is just a set of coordinates really, where you can see that the number which is shown is basically defining us the coordinate of its lower left edge. And we can therefore take this texture and map it on various objects in a way as if you would be, you can imagine as if you would be projecting with a projector an image on some geometry. This geometry could be a plane, like a canvas, and then your projections will be undistorted. But if you will be projecting on some three-dimensional object, these projections might result into some distortion of this projected image, which might be desired or not. So the planar projection is the simplest projection, and you can imagine how this can be defined. So we will have certain object, and then we will define a certain direction from which we are sort of mapping a particular texture. And of course, we need to define how big, how are we stretching this texture when we are mapping it and projecting it onto this object. And we can, of course, have various projection types, like the parallel projection or the perspective projection, where we will need to deal with the perspective foreshortening. And we know all this pipeline already, because this texture mapping approach will be more or less identical with the viewing transformation approach. And then there are some other approaches of projection, like, for example, the spherical projection approach or a cylindrical projection. So if we have some objects, let's say we want to make a nice texture of a potato, then perhaps a spherical projection could be a good approximation. If we have an object which should be a stone, or everything which is somehow round and isotropic in its extent, probably the spherical projection would be a good way of mapping the texture coordinates onto the object. The idea would be that we are having a sphere, and in the sphere we have our object, which is roughly a sphere, and then we will be mapping the coordinates of the of this surface. We will be finding out the texture coordinates by basically finding out the parametrization of the sphere and transferring that parametrization of the texture onto this object. The same will be done for cylindrical projection for objects which will be elongated in one direction. So if we will have a hand, for example, then maybe the hand would be nicely parametrized by a cylinder, or at least maybe just a forearm. And then we can apply a cylindrical projection on that part and apply, for example, some texture of a skin. A different projection to spherical projection is the cube map projection, which also somehow is aiming at, especially if the cube is isotropic and it's not a box which is elongated in one direction. The cube maps are beneficial because in their projection we can also define the texture coordinates based on this cube map. And the basis is not a sphere, but a cube. And it has discontinuities, but it doesn't have the very drastic discontinuities as the spherical projection. We will talk about this in a moment. So let's have a look at the planar projection. We can see here that what we want to obtain are the UV coordinates, and what we have at the beginning is the world space coordinates, x, y, z. So this is our object. We already know that this is the homogeneous coordinate element in both cases. This would be the z value, but the z is not really interesting for us because we are dealing with 2D textures. So we will be basically applying the same UV coordinates for all elements which have the same spatial extent with the same values of x, y, z, but with the different xy but with the different z value. So you can see here how texture parametrization is realized. So here is the UV parametrization, U and V on the image, and this image is basically projected in an orthographic projection on our object. Our object, which we are interested to sort of projected on, is not perfectly straight, it's curvy, but that's okay. The texture will be slightly deformed, but nothing serious. So the same goal from the world coordinates, we want to get to UV, which will really be similar to these normalized device coordinates. You remember? Those were from -1 to 1. In our case, we would be interested into coordinates which are from 0 to 1, but there is just a minor change. The conceptual implementation will be the same. And we see here the transformation. So we really are somehow in this world space, in this stage, with our XYZ coordinates, and need to perform the camera transformation. We need to perform the projection transformation, and then we are reaching this normalized device coordinates or this canonical view volume. That's where we want to basically end up. Keep in mind that we are not really dealing with a camera transformation or camera space for a camera, but from a direction from which we are applying our 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 texture. So this is not a viewing vector. This is a vector which is the direction of applying the texture. It can align with the viewing vector sometimes, but it doesn't have to. So I took these formulas from our viewing lecture just to remind us what is the camera transformation, how we can transform from the world coordinates to the coordinates of the camera space. These are the U, V, and W vectors. And this is the eye point position, which we would basically need to define. And from that, we will be able to realize our camera transformation. So this is an inverse matrix to that. Then we will be able to go from the world coordinates to the camera, from world space to the camera space. So you can see here, here is the U as a transpose, here is the V transpose, here is the W transpose vectors, and this is the minus E vector, column vector. So this is the eye point position. The graphic here is showing that we are basically aligning now our camera space with the world space so that our eye position is aligned with the origin of our world coordinate system. The next step will be for orthographic projection, we will perform the same transformation as in the viewing pipeline, where we will be just scaling our scene into the by the factor of between left and right, top and bottom, and near and far, which are the same values coming from the viewing pipeline for correspondence. In our case, this will be the borders of how broad our texture should be. And this will not be, the near and far will not be very relevant, but the left and right and top and bottom will basically define as the extent for stretch or shrink our texture, which is supposed to be projected. Unlike in the previous case, where our normalized device coordinates ended up to be in the range -1, 1, here we are ending up in the range 0, 1, and therefore the scaling parameter here in the denominator will be 1 instead of 2. Otherwise, the transformation will be very similar to the transformation of orthographic projection transformation we have used for the viewing purposes. And here we can see the result. So by applying the camera transformation, of course, not the viewing vector, but the direction along which the texture is being projected, and then the orthographic projection, slightly modified, is applied, and we obtain from our world coordinate values, we get our texture coordinates, which we then use for the texture mapping. So for each point on the cube, we know their XYZ values. We process them, multiply them with this complex matrix, or this matrix which is pre-multiplied, and then the result will be the UV values. These UV values we will then use for fetching the corresponding texel within the texture. So this is the planar projection, exactly in the same way as in the viewing transformation. We can extend the concept of orthographic projection, to the parallel projection, to the perspective projection, where we have to add one more matrix. This one more matrix will be this projective matrix, which is necessary to extend the orthographic transformation and by multiplying that transformation with the perspective projection matrix. You might remember this small image here, where we were, based on the similarity of two triangles, we were defining how we will change the one of the coordinates based on the perspective, the so-called perspective foreshortening. So the principle was that we have two triangles and their mutual correspondence was expressed by that the ratio between the sides remained the same. So the ratio between the big triangle here, which was the y divided by z in this image, was equal to ys, the coordinate of y, which is projected onto the viewing plane, divided by d, which was this near plane at the end. So, and in order to find out the ys, the ys was then equal to d times y divided by z. And this way we were able to compute the size or the scaling of our coordinates onto the viewing plane. And we can use the same concept here in order to find out what we are projecting on our, which pixel will be projected to the particular object in the 3D scene. So for that, we will need a setup which will define us somehow not only the projection direction, but also the perspective would need to be expressed somehow. For example, by defining the near plane and also having the eye point available. So the near plane will be then equal to this D, which we were using, and that will be used for scaling. And we can see here that in the fourth row, this one here in the perspective projection matrix will store us the z distance, which we will use then later for for dividing and to find out the actual UV coordinates. Again, the information about the z we can neglect now because we are not interested really in the new z coordinate because our texture is parameterized just by the u and v. And the w will be then used for the scaling because we need the scaled parameters in order to perform the texture fetch. Otherwise, we will not have the perspective foreshortening. So this was a planar projection which can be used for mapping textures onto objects, onto planar objects or also to objects which are not planar. And we will by that simulate as if we will be projecting some image as we do with the projector, as we can do in the projector in the real world scenarios. Another projection type, as I mentioned, is the spherical projection, a very popular method which is basically using the parametrization of a sphere and its latitude and longitude angles to become the u and v parameters. So this will be the u and this will be the v parameters, and then using this parametrization for mapping this parametrization onto the surface. So as I sketched it already for you, we will have some object here, and this object will then be adopting the u and v parameters from the sphere parametrization onto its surface and by that we will define the texture coordinates. These texture coordinates will be then mapped to a UV texture, and the texture fetch will be performed. All great. However, there is a problem. There are two discontinuities which might result into rather nasty artifacts, and those are the poles. So in the pole, near the pole area, there will be a distortion which will be significant, and the texture in the UV parameterization would significantly need to compensate for that. And there will be a lot of pixels spent for the region near the poles in order to sort of avoid this distortion. So this is an inefficiency. However, the rest of the sphere will be actually mapped quite nicely. So if there are two sort of unimportant regions where this where the poles could be placed on the sphere or on the object, which are not that visible perhaps, or not so significant, then perhaps this would be a good mapping. So as we mentioned, we will be taking the latitude and longitude angles as a parameterization, and we will use them for parameterizing the point on the surface of our object. Let's have a look how this can be computed. So again, this is our object now, which we see here, the cube with the rounded edges. And this cube, we would like to map with some texture using the spherical parameter projection. And we can see here how we can obtain the U and V values. U and V, actually it's written here already. So the U and V is can be obtained from the two angles which I mentioned, and these two angles can be obtained actually from the Cartesian coordinates XYZ of the position on the surface of this object. So what is happening here? Let's draw us a sphere for a moment so that we get some kind of intuition here. And we can see that there is, if this is a sphere center, and maybe this is a zero angle for the, okay, so this will be the phi, and this will be, so this is an angle phi and this is an angle theta. Now, we are using these two angles for the parameterization. And imagine that this is a sphere which the sort of the equator lies in the xy plane. So this is an xy plane where x and y is here, and this and the origin, in fact, is located at the center of the sphere. So then, if that's the case, then for our object, if we take the y and the x coordinates of certain point in the space, so let's say that this is our point, which has then is then projected onto the and is having this phi angle spanning with the one of the axes, the y-axis here. In such a case, we can compute this angle phi by the 8 and 2 function. Remember? So this 8 and 2 function can be useful to get the value phi. So this would be the phi. But actually, we are not so much interested into phi, which would go from, as you know, minus pi to pi, but we want that it goes from 0 to 1. So therefore, a little bit more is necessary to be done. So therefore, we are scaling the phi with the 2 pi, which will bring the values from minus 0.5 to plus 0.5. This will be now the outcome of the fraction. And if we add 0.5 to it, our interval from minus 0.5 to 0.5 will change from desired 0 to 1. So this is how the first coordinate, the u coordinate, can be defined. And then let's define the v coordinate now. The v coordinate is this other spherical coordinate angle, theta, which is changing between 0, so this will be the 0 then, and actually going from 0 to pi. So theta goes from 0 to pi. Okay, and so for example, if the z is 1, that would be in this case, then and then xy is 0 and z is 1. So this is 1 divided by 1. This is 1. Cosine, that corresponds to cosine of 0 degrees. So this is correct, this is here. And if we will have the value, let's say z equals to 0, z equals to 0 will be in the xy plane, then, and let's say the x will be 1 and y will be 0, then we will have 0 divided by 1, 0, 0, so 0 divided by 1 is 0, and the arcus cosine of that will be pi half. And then if the z will be minus 1, then we will end up in the value for theta will be pi. So here we have a relatively simple job to normalize it to the region of 0 and 1, because we will just divide it by pi and then we are done. Simple like that, we obtain the v coordinate, which goes from 0 to 1. Keep in mind that these are the coordinates of our object in the scene, but these coordinates of the object in the scene can be nicely mapped into these angles, and these angles then correspond to a particular position on the sphere. And these positions we will then use for our parametrization on the surface. So while we are using sphere as an object as a proxy object, and to fetch the u and v, we will apply this texture parametrization not on a sphere, but on the actual object, which is supposed to be textured. So that was a spherical parametrization. Now let's have a look at the cylindrical parametrization, which would be more useful for objects which are elongated in one dimension. Such a parametrization will be very, very analogous to our previous case, just that the u parameter we will obtain exactly in the same way, because we will be performing the u parametrization around our cylinder, and then the second parameter v will be very close to parameterizing the z to the z-axis, in fact, which is the one if the x and y axes are here, and this is the z-axis. This will be our situation. So we can see that the parametrization of the z should then go, the v should go from 0 to 1 in this way. In this way, it was from 0 to 1 like this, around, and for the cylindrical parametrization for the v, the parametrization from 0 to 1 for the v should go along the z-axis. I maybe forgot to mention that also in the previous case, we were considering that our space is constrained by the -1, 1, where our object is, and that is in all 3 dimensions. So our center point will be in the position 0, 0, 0, from which we are starting our parametrization. Now, for the u, you can see that we apply exactly the same formula, where we are first finding out the angle, then we are normalizing that angle to -half to half, and then we are shifting with the 0.5 so that it is in the range 0 to 1. The v is changing, and as you can see here, the z will be going from -1 to 1, and in order to get the v from 0 to 1, we are now dividing the z by 2, so the range is now shrinking from 0.5 to 0.5, plus 0.5 will be our desired range from 0 to 1. So this is a simple extension of the spherical projection, or adaptation of the spherical projection for the cylindrical projection. And then in our scene, we can decide which objects should be parametrized, texture parametrized by the cylinder, and which by the sphere. If we will be deciding that our texture, which we have been using, these numbers, remember from the planar projection and parametrization example, here we will be using the spherical projection, and we will see that the disadvantage is that while the texture is close to the z equals 0 is relatively stretched, so sorry, it's shrunk. Here the texture is much more dilated, so the numbers are getting bigger, are scaled in one direction, and that is just because that was the spherical parametrization. But if we will be using the cylindrical parametrization, as it can be seen in this case here, we can see that the parametrization is actually quite nice, and the numbers on the texture has been not stretched or deformed by this parametrization, because this fragment of is actually quite well aligned with a cylinder. Sometimes, instead of spherical projection, we can use another approach, which is called cube maps, which can be used for the texture parametrization function. Cube maps have the advantage over spherical projection that while they create more discontinuities, those discontinuities are not very significant, are not that drastic, as the spherical projection discontinuities, or spherical mapping discontinuities on the poles. The discontinuities or the distortion which is created through the cube maps is just always where 2 faces are meeting in an edge. There is a small distortion, but often this doesn't lead to any noticeable artifacts. Cube maps are also easier to compute, and they can be also used for so-called environment mapping. So not only for texture mapping, but also for sort of representing an environment nearby our object. We will be talking about environment mapping at the end of this lecture. So how to compute cube maps? essentially, we can compute them in a similar way as we were computing the spherical parametrization. However, here we will have to deal with each of the 6 faces individually. So what we do is also in the same way as previously, we will be having our center position into and we will have a cube which is from -1 -1 -1 -1 cubed. And here we have 1 cubed. And within this region, we will place our object which we want to perform the texture parametrization on, and possibly to apply a certain texture which is represented on the sides of this cube map. Now, for each point on our object, we will connect it with the center, with the origin of our coordinate system, and then this vector we will simply extend so that we calculate which of the sides is being now intersected. So here this will be the bottom side. Here this intersection will lead to the top side. This intersection here leads to the front. And this will be probably the right, and so on. Now, so we always need to define which intersection are we interested in. And then we will take that for that particular ray or for that particular position on the surface, we will pick one of the 6 faces and perform the texture mapping. The function, again, of the texture map goes from it results into 0, 1. And now, imagine if we hit our object, if we hit our face, then we will be able to perform the parametrization from 0 to 1 by calculating the y from the y coordinate and from the z coordinate in case of the so-called x plus phase. So the x plus phase, it will be the one. This is the x plus phase. And imagine that you are a person who is standing inside this cube. And when you are looking at the parametrization, for you, from this perspective, the coordinate system should look approximately like this. So the UV parametrization should be something like this. So the Z goes to the positive direction. This is the Z. And the Y goes to the negative direction. You see, this is the Y, which is going into the right face, as I called it. So this will be minus Y direction. And that is also what we have here. Then, furthermore, we have here the value 2, because we want to, from the range, if we will be on the face, we will have we will be within the range from -1 to 1, which the values of the y and z can reach. So we want to, again, shrink it into the region of 0, 1. So we first shrink it to -0.5 and 0.5 with this denominator, and then plus 1/2 will lead to the correct range of 0 to 1. One thing we need to note, what is this x here? This x here helps us to actually perform the parametrization without the need of the necessity of hitting the intersection at the position of the where the face is. We can directly from the 3D position of our point in space, we can define our texture mapping function coordinates. And this x is a scaling factor here in the same way as we perform the scaling factor in the case of the perspective projection. You remember? Just a few slides back, we were using this what we learned within the viewing transformation lecture, we were dividing by the z. But here we are not dividing by the z, but because here, in this case, for the face plus x plus, we have the line along which this linear perspective shrinking should happen is the x-axis. Therefore, the x is the denominator and will shrink us or actually extend our values for y and z to the correct values so that we do not need the necessity of performing the intersection test with the x plus face, but we can calculate the coordinates directly from the 3D position of the object itself, or 3D position of the object's surface points. Now, in the same way, we see the logic how we perform the parametrization for the x minus phase. So this will be the x minus phase. And here we see that the z still, if we parameterize this image, will go towards the top. That's the z plus direction. And here we will have the y plus. So this is the y and this is the z. And exactly we can see that also here in the formula. Other than that, the formula stays the same. And we can recognize the same pattern again and again. So for plus y, where do we have plus y? This would be this face. I will show this example as a last example. This will be this face. Here we have again plus z will be one texture coordinate, and the other one will be plus x. This is this direction, you see? So this is plus x. And again, we are dividing by 2 because we want to get into the range of minus 0.5 plus 0.5 plus 0.5 bring us to the 0, 1 range, and the y is here so that we can again perform this scaling with the y value so that we do not need to actually calculate the intersection point with the y face. Okay, so hopefully this was clear. I will not continue for all the faces, but you can see the analogy, how this works for all faces. We first, for the cube maps, need to find out which face will be used for the texture mapping, and once we obtain that information, then we perform simply the texture mapping UV coordinate computation based on which face are we dealing with. Now we are coming to another set of texturing where we have somehow a texture already, or texture mapping function already given, and for the triangle mesh we will define the texture coordinate function on the vertices. So each vertex, besides its position in 3D space and perhaps a normal and a color, will be given a particular values of the texture coordinates, the UV coordinates. And for this, vertex here. Let's call it 1. The U will be 0.2, and the V will be also 0.2. For number 2, this will be, which one is number 2? Well, it's this one. Number 2 is here, and it has 0.4 in the in the U direction and 0.8 in the V direction. So this is how we define the texture coordinates for our triangles. And if we want to create a continuous texturing of our object, like for example we see on this image here, then we make sure that our texture mapping is continuous across the triangles, across the faces. And we ensure that by having the same texture coordinates on the vertices for, for the neighboring triangles. This means that each vertex is having the same value of the texture coordinates, and this ensures us that we will have a continuity in the texture mapping. So, and what do we do once we have the values available at these points? Well, then we can texture map those points, those vertices. But that would not be enough, would it? Well, as with everything what we have done in the graphics pipeline, the rasterizer will help us to get the correct values also within the faces. So exactly as we can rasterize or interpolate the values for color or normal or a position, in the same way we can interpolate the values of the texture coordinates. And once we interpolate, then for each point, for each fragment, we will have a particular texture coordinates, which we can then use for the texture fetch to obtain the color at that particular location. For texturing, we have, as we said, we have to ensure that our texture is somehow uniformly distributed for the triangle mesh which we have. Because if it's not, then we will have some triangles represented by a lot of texture information, by a lot of texels, and some will be represented by very little ones. We can see such an example on the face, where we typically have a problem with some extrusions, such as nose, for example, where the texture space is actually very small for the nose, which spans, in fact, a relatively large area. We can see it on this texture image, which would be with the texture mapping, where it shows how much each triangle takes space on the texture. And we see that for the nose and for the eye region, this is actually quite little. There are other properties. So that is this aspect which I was talking about. There are other aspects for having good texture mapping with interpolated texture coordinates for the meshes. There should be a continuity, and as I said, this can be ensured just by that the vertices have the same vertex coordinate, that the vertex which is shared among the faces or edges have the same vertex coordinates for each edge or for each face, which are adjacent to each other. Injectivity will be the condition here that the texture appears only once on the surface. So we do not have any repetitions, which we will then find as disturbing. On maybe organic structures, this might be a little bit disturbing if we will see some see some regular repetitive pattern. For man-made objects, like for example a brick wall, this would be much less disturbing and actually desired. And also, what we would like to avoid is that not only the uh, shape, the size distortion is not very significant among triangles, but also that the triangles on which we map the texture and the triangles which are then projected into the texture space, that they look approximately similar, so that our texture mapping is not leading into very much distorted shapes. Furthermore, especially for, as I said, man-made objects where a repetition is desired, we have possibilities of defining the texture coordinates outside the range of 0, 1. So far we have been talking about this region, this range of a texture mapping, but you can imagine, for example, that we have a texture coordinate which is, for example, -1, -1. And what should we do with that? So there are several modes which we can turn on, so to say, for texturing in order to define what the texture should be doing outside the range of 0, 0, 1, 1. So one option is, for example, padding. The padding would mean that we are just giving it a background color. So for padding, this is equal to background color or some white color, which, for example, could be used if we would like to, for example, put some logo on a relatively large geometry. Then we would not want to stretch it all over the geometry, but just in the center. And for this, such a padding would be a good idea. Clamping is another approach, which is giving you the option to, for example, to use the last value of your texture and sort of spread it out all over from the border. So this will be the clamping mode of what to do outside. So if there is some kind of a brown color on the border, the same brown color will be then propagated from the border or from the zero value, for example, in this case, towards all the negative values. This is, for example, useful if you want to perform some filtering, then and we do not want to change the filter kernel on the regions where the filter kernel is just like only halfway in the image. So we will just perform the clamping so that the filter kernel can actually fetch the same values which would be otherwise on the border. The next approach, so this is for filtering, often used. Then the next approach is styling. And that's this approach we can see actually in this case. So our texture will be simply repeated again and again as if we would be performing the modulo operation. Probably this is also how it could be realized in some sense. So this is useful for performing some repetition of bricks and so on, but you can still see also here that it is quite apparent how the repetition is done, and it looks a little bit unnatural. And the last mode of how the texture coordinates can be defined outside the range 0, 1 is mirroring. So that would mean that we will simply mirror, let's say on this will be the axis of mirroring, and we will simply mirror the image outside against this axis. against this line, which means that this white stripe would extend here, as you can imagine, and so on. So you can imagine how the mirroring will look like, and this leads to a little bit more continuity within the textures, because the structures are not interrupted but are actually elongated across the 0-1 range. One thing which we need to properly care about is if we have our scene rendered, we are actually performing the rasterization and the interpolation in the screen space. And if we are performing the interpolation in the screen space, then we might actually have some problems with the texture mapping. Imagine that what you see here is actually a long rectangle consisting of several tiles. The tiles are of the same size, but it's this rectangle is very we see a very slanted view, so we see it from the very side. And these tiles, this tiling here is actually the texture. So which of these two texture mappings you think is correct? If we see this rectangle, large rectangle, in a perspectively correct view. Is it this one is the correct, or is it this one? What do you think? Well, you can see here the difference is that this distance is much bigger than this distance and this distance and so on. While here, these distances are actually the same. And this is, so I can already tell you, for the perspective foreshortening, of course, this one is the correct one and this one is the wrong one. But the rasterizer doesn't really know much about the perspective foreshortening. And if you have the texture coordinates defined on the vertices only, then it will perform the interpolation in such a way which will result in this mapping. And this is a problem. So we need to somehow deal with this issue and make sure that our texture coordinates are carrying with itself this notion of perspective foreshortening. How can we do it? Well, let's see. It's shown here on this little pseudocode where we can see that actually we are using the, let's see, this homogeneous coordinate for each vertex. So we have vertices 1, 2, and 3 because we are dealing with some triangle. Although the triangle is not shown here in this pseudocode, we do have a triangle. And here we are calculating the barycentric coordinates, as you can see, for the screen space x and y coordinates. But we are keeping in mind our perspective homogeneous coordinates are still available here. So in our, you remember, our value, so we have in our vertex, we store the x, y, z value and w, and then we also store there the u and v. And so actually, sorry, for the triangle we have here three sides, 1, 0, 1, and 2, not in this. So the 0 here is associated with the vertex 0. Now, so we store both the u coordinates and the w coordinates as the other coordinates as well. And we are now calculating, interpolating with barycentric coordinates alpha, beta, and gamma among these three vertices 0, 1, and 2, the u coordinate as an barycentric coordinates interpolation. But we are performing this, these are the so-called screen space coordinates of the u and v, which are calculated here. And also, we are performing barycentric coordinates calculation for the homogeneous coordinate or reciprocal of it. So that we have, at the end, we have calculated this this barycentric coordinate of this element, but the reciprocal of it. And then we perform what we could call anti-homogenization, where we divide by this factor 1s and convert these screen space coordinates, these coordinates, the wrong ones, into the correct u and v coordinates, which will then create for us the correct parametrization, which will be perspectively correct. So then, once we are performing drawing, we will be drawing on the screen space coordinate x, s, y, s with the color of the texture at the position u and v, which we calculated. So this is an important aspect, how to keep the texture parametrization to support the perspective. One more thing we have to keep in mind when we perform the texture interpolation across our triangles is how to do it across seams. So we already discussed that for a closed object, we will have a seam at some point. And in a parametrization, when we have a longitude with on the globe, we will have a discontinuity because longitudes are at some point changing from plus 180 to minus 180, from plus pi to minus pi. And this will cause an abrupt change, which will lead to the fact that our texture interpolation will then go because we have the same, we are keeping the continuity. This continuity is now fighting against us because if you are trying to interpolate between minus 100 and plus 100, then you will actually go backwards through the entire texture and interpolate like this. So what you are seeing here in our interpolation at this position is that for all these triangles we were actually crossing here both Africa as a continent and South America, and that is causing these two stripes of artifacts. For this to solve, what we would need to do is to at the seam duplicate the vertices and assign for those duplicated vertices their positive values, so that interpolation never happens across the seam, but that the interpolation then performs within the negative values or within the positive values. So this is important to keep in mind, and it has been solved in this case on this picture where there has been added another layer of triangles. The triangles have been duplicated so that they are having the same values as the and so that the interpolation is performed correctly and doesn't go across the entire texture image. So across the seams, we need to duplicate the vertices. Now, we have already covered how to perform the texture fetch through defining certain texture functions which deal with the parametrization of a surface onto the 2D image texture space. Then we have been dealing with how to actually stretch such textures across triangle meshes by defining the texture coordinates on the vertices. And yet, our results will be still very low quality with the texture fetching which we have currently presented. And the reason is because we are not performing any filtering, and so far we are performing by the texture fetches as defined just the nearest neighbor sampling. We will be always rounding up to certain pixel or texel in this texture value, and that one will be shown. So this will lead to artifacts where if we are magnifying the texture, there will be some staircase artifacts. And if we will have the texture mapped to large regions of a texture mapped to a very small finally rendered image, we will end up in some moire patterns. Therefore, we need to properly filter the texture result so that all these effects will be suppressed. One way to deal with it will be through supersampling. This could be done at least to some degree for the when we are having a large area of a texture mapped onto a small area in the finally rendered image. The supersampling will be a solution, and then we will take the average of the value of this supersampling. So how can we perform a good filtering of our texture so that these artifacts are not happening? Remember, here there would be the staircase artifacts, and here would be the moire patterns. This can be done through analysis of what is the area behind a particular pixel. So we can take for one pixel, let's say that this is our one pixel of fragment with its four edges, and we can perform the calculation without any rounding into our texture space, what will be its position. And then if we connect these four different points, we can see what is the footprint on the texture. So the footprint on the texture for this one pixel will be actually even a smaller footprint in the texture space. So we are in fact magnifying the texture so that to generate the texturing in this area. If we will be, as I said, performing just nearest neighbor interpolation, that will lead to this ugly staircasing. And the same holds for even closer fragment here, where the 4 points will map to even smaller footprint on the texture. But these are not the most interesting footprints. What if we look here at this example? It maps actually into a very anisotropic shape, uh, which will be then, if we want to represent the texture in this position, in this one uh, fragment, then we will need to actually average this entire area of the texture and not just take one point, maybe in the middle, because that will create us these moire effects, this moire artifact effect. So we can see that the more far away we are, the more extruded this or anisotropic the footprints of these pixels are. And how can we calculate these footprints? It can be calculated by performing an inverse viewing transformation first, so that from the individual positions of these fragments in the screen space, we get to the actual 3D positions in the world space. And then from this 3D position in the world space, we will perform the texture mapping function, which will bring us into the texture space. So we get from 2D space to 2D space over the 3D space of the world scene. So I already told you the secret what to do in order to get rid of the moire effects. We need to basically calculate the overall footprint of our pixel on the in the texture space and then perform the actual averaging. However, one thing which I didn't tell you is that in some cases this mapping of um, the pixel onto the texture space results into very wild shapes. And this calculation will be highly computationally inefficient. Therefore, instead, we will be performing an approximation of the area which has to be filtered or averaged, and this will be done by the principle of Taylor expansion series, which I will touch upon very shortly in a moment. In short, what we want to achieve is we want to compute the center of our um, uh, texture fetch, so the center position of our pixel, and also we will store in our um, in a matrix, the Jacobian matrix, the partial derivatives of how does the function from image space to texture space, how does it locally change. And we will only have a first order derivative approximation of it, so a linear component will be added to this central point. And this will be then used for calculating how does which direction does the pixel uh, stretch in the texture space and by how much. So let's have a look at this Taylor expansion series, which you should have heard about in the calculus in your undergraduate studies. This is a methodology how you can, through the derivatives or uh, of a function, create an approximation, or actually you can reach the value of a particular function. So what is represented here? Let's say there is a function f which is very complicated to calculate, and we don't know its value at the position x, but we do know the value of this function at the position a. And we also, therefore, and we also know what is the first order derivative of this function, second order derivative of this function at this point A. So if we know that, we can create this series, this sequence, this sum of a weighting factor and then of some polynomial, which will then in sum be going closer and closer to the value of fx, which is the one which we have hard time to calculate normally, and we can calculate it through this approximation process. So for example, we can have a look at just for exercise at the function ln x. ln x is maybe hard to calculate at the position x, but maybe the ln is not hard to calculate at some given position. For example, of ln a, where the a will be equal to 1. When a is equal to 1, ln a is equal to 0. We know that. So we could calculate ln x in the following way. Is equal to, and here the sum will be ln a, and then this is 0th derivative because j is 0 here first, and then divided by j factorial. 0 factorial is agreed to be 1, and here 0 means that this term will be 1. So ln a is at the beginning, and then plus, because we are realizing this sum, and then first order derivative of ln will be 1 divided by, so reciprocal, 1 divided by a, and then divided by j powered by 1, so, sorry, j factorial, so, which means 1, and this whole times x minus a. So this is an approximation with a linear term here. If we do not expand the series even further, how can we approximate the value of ln x at the particular position x, which we don't know, maybe let's say 1.5. Okay, so this is how we calculate the approximation with the Taylor expansion series. And I'm explaining this to you because we will be doing something like that here. We will be using the Jacobian matrix, which is expressing us the partial derivatives of the x in the texture space, UV texture space. So if I'm changing a little bit in the x direction, how much will I change in the u, and how much will I change in the v? So how much does the change of x change in the u and v? And we can see that this will be in this case, so here is our central position, and we can see that this is the approximation, the linear approximation of this function. Our mapping of our pixel on the texture space is this complex shape, but we approximate it just by this parallelogram. And this parallelogram, to find out, we are using the partial derivatives from this function of these two transformations, inverse viewing transformation and then the texture mapping transformation. And then if we change u and we change x, it can change, and most likely will, in both u and v direction, because the u and v and x and y are not aligned, so both are changed. And the same holds for the changes of the um, of the um, when we are changing in the y direction, and we can see how does that change in the texture space. Once we have this information, we can approximate the footprint of our pixel and in the texture space, and then we can perform the averaging. And this averaging is performed not on this wild shape, but on the shape which is which is this parallelogram. Still, it might be quite complex because if we have an object, um, if we have a mapping like this, so very small area in the image, but very large texture area to sample, we maybe do not want to perform this sampling, and we might want to do something something else instead, and we indeed will, as we will show on the next slides. So let's have a look before that at a different example. In the example where the pixel is actually magnifying our texture in some area. And if we do not perform any filtering, then our magnification will result into this nearest neighbor approach where there will be heavy staircase artifacts. So what we need to do is to, for our central pixel position, we need to calculate its value. And instead of taking just the nearest neighbor, which will be this texel, we actually take all its 4 neighbors and perform bilinear interpolation to find out what is its value. And this bilinear interpolation then helps us to make a more continuous transition without hard, edgy artifacts. We can also perform a more complex filtering, like a bicubic one, which will be even smoother. However, that will likely come with some additional costs. In the code on the left, you can see how such a bilinear interpolation can be realized. So for particular coordinates u and v, we will be calculating first what is the pixel which corresponds to or what is the position in the picture which corresponds to the values which relate to its resolution. So here we will not go from 0 to 1, but if the texture is 512 times 512, we will be going into the values between 0 and 512, or actually minus 0.5 and 511.5. And once this is calculated, we can calculate its nearest neighbor by this floor operation, or not its nearest neighbor actually, but the lowest neighbor. So it will be actually the floor will point to this value. And then we will be calculating both for v and u the other 2 neighbors. So now we calculate the coordinates for all 4 neighbors. And then we are performing our first linear interpolation of u and v, and then we perform another linear operation of these values and perform the texture fetch in this case here, and based on these calculated weights which are associated with each texture position. And this way we can create the bilinear interpolation within a texture and solve for the magnification cases. But for the minification cases, we need a different solution because the supersampling will be simply very time consuming. The solution is called the MIP mapping. The MIP mapping, you have probably heard about MIP mapping before, didn't you? It is an approach where we simply represent one image by a stack of lower resolution images forming this kind of a pyramid. So this will be half of a resolution, and this will be another half of a resolution, another half of a resolution, and so on. We have it's shown here where we are always performing a resampling on a half resolution. Now, once we have such a pyramid, then we can surely find an area where our um, where our pixel is in some of these levels mapping to an area which is actually smaller. So we again would perform a magnification, a bilinear interpolation between the neighboring samples, and by that reconstruct the filtered value. So this looks like we are losing a lot of information, but actually, no, we are not, because we are performing averaging, and that is over the entire area, and that is exactly what we would be doing. So we would need to find out on which level of this pyramid we need to perform the bilinear lookup, and then we will, once this bilinear lookup is performed, we are using this value for texturing that area, which would be the filtered one. What we could also do is we can find the upper and the lower levels of between which the our texture is our pixel is being between bigger and smaller than one pixel size, and then we can perform a bilinear lookup in these both levels, and then perform a final trilinear interpolation between these levels to perform even higher quality averaging. It will, of course, come with some computational overhead. And it sounds very complicated because we need to not only perform this averaging, but we also need to find for a particular footprint which level we should perform the bilinear interpolation for, etc., which all is possible to do, but it's a complicated code. The good thing is that all this is already implemented for you in the hardware. You just need to enable the mid mapping, and all these procedures are being done for you. So, and it will be done in a very computationally efficient way because the hardware implementation leads to a very performant operations. Nevertheless, we still need to understand what is the hardware doing. Remember, this lecture is about to understand the low-level mechanisms and algorithms in computer graphics. So even if we would be using our rasterizer for performing all the texturing for us, or the GPU or the API, which we will be using, either DirectX, OpenGL, Vulkan, etc., there will be all these operations performed for us, but we need to know what is the hardware actually doing. In this code, you can see the trilinear interpolation, which I was mentioning to you, which would lead to even better values of the filtering operation. And you can see that there are several examples of this grazing angle texturing. So this is the high resolution image where there was, it's just a reference to show the correct solution. Here we see the point sampling with the nearest neighbor sampling, which leads to these heavy artifacts. We can see here the trilinear MIB mapping as discussed in this, as discussed previously and shown on this pseudocode. You can see here that we first perform the calculation of which level we should be interpolating on, and then we find the two levels in between, perform the bilinear interpolation on both of these mipmap levels, and then perform the trilinear interpolation as the final step. The MIP mapping, I don't know if you have thought about it during the explanation, however, is an isotropic smoothing or isotropic subsampling. That means that if our texture fetch is highly anisotropic, leads to these long, elongated, thin footprints, our map will not be able to match this footprint very well because it will be isotropically increasing the region on which we perform the filtering, on which this averaging is being performed for us. So that is not really desired always. And what we can think about is that we will divide this footprint into isotropic regions and then perform the filtering operation for each of these isotropic regions on a dedicated level of a MIP map together, and then perform the averaging of these isotropic regions so that we have an isotropic filtering performed at that position. So that will be the highest precision of our filtering, and that is shown in the final image here, which you can see that it's a little bit sharper than the trilinear mapping, but it's a question whether it is worth the costs. Computer graphics has been using texturing not only for the purpose, its original purpose of texturing an image on a sort of constantly colored geometry, but also that the texture can actually carry different information than just a different color at a particular position. For example, here in this case, we can use the texturing for both putting the logo of the university on a cup of the cup geometry, but at the same time, the texture can contain an material properties as well, which would mean that at the region of a texture, which will be then in the area which is filled with red, there will be also a different values for the material properties. So if you think of a mug with a logo printed on it, you can imagine that the mug itself is very shiny and specular and glossy. However, the logo is more of a matte type. The print is not so shiny. And this information can be carried in the texture as well. You remember perhaps that the material properties were defined by some Ka, Kd, and Ks, which together were equal to 1. And these properties were used to define how much is the surface of an object what is the material? Is it more glossy material? Is it more diffuse? And so on. So with these three values can be stored in a texture instead of the color values. Or we can have two textures, and in one texture we are having the color values, and in another texture we will have at the corresponding locations we will have the different material values. And actually the material can also vary from pixel to pixel, exactly as the color reflectance is varying from pixel to pixel. So here we already can see a different application of the of the texturing, not only to transfer or augment the object with different reflectance, but also with the different material property. Another example of how a texture can be used is to perform the so-called normal mapping and bump mapping. So these terms mean that we are actually storing in our texture a small changes of the surface in order to not to have such detail stored in the geometry itself, but only that this detail is present and used during the shading. So you can imagine that you have some flat um, area as this floor in this case, and then we will have some bump map which will locally say that the surface should go a little bit up and a little bit go down and then up and then down. And in this bump map, we do not really move this surface in any way. That is not what's being done. Actually, what we do, we perform the texture fetch and we know what the displacement should be with respect to the normal of our plane or of our geometric primitive. But based on this bump map, we actually calculate the normal map out of it. The bump map, as you can see here, defines normal map indirectly through its derivative. So if we derive the bump map, which could be, for example, done by some Sobel filter first order derivative filter in one direction, in another direction, we can calculate that this bump map will then turn into a normal map, and then at each position we will have a calculation of a normal change with respect to our normal, which is defined for the geometry. So we need to somehow anchor these or relate these normals to the main normal of the geometry, and there will be then some small changes of the normals which will then encode a more complex geometry, but this geometry encoding will be only visual. There will be only normal change, but not the surface itself, which means that in the shading, the normals will be used for calculation, but actually the surface will not be changed. So it will only look like a more complex geometry, but in reality it will not be. So you can see that we can have for texturing several textures. One texture will be the color texture. Another texture can be the roughness texture, which would mean that the texture is defining as different levels of specularity. If you look at some wooden floor, at the tiles, some parts of the wood are soaking in the lac in a more stronger way, and some areas are not soaking it that strongly. So there will be some rougher areas of the wood and some more glossy. And exactly this can be encoded by material properties, the K, A, K, D, and Ks in the roughness texture. And then we will have the third bump map texture, which will be then turned into a normal map. And this normal map will will give us these small changes here, like for example, the small imprecisions on how these tiles are connected to each other, as we can see. This geometry will not be changed in reality or in the scene really, it will be changed only through the normals. So the normals will be changed and the shading will then be affected, but not the geometry itself. We can see here two different approaches between changing the geometry appearance with the bump maps or normal maps and the so-called displacement maps. So this example here is showing us a bump map, and we see that this doesn't look realistic at all. And why is it the case? The reason is because the contour is showing us that that there was no displacement really happening. It was always still a very perfect shape. Only in the regions outside the contour, it looks like it is more rough. If we would hide, sorry, let's try to do that. Let's hide this area. Let's pretend we don't really see it. And if we see just this part, now it starts to look a little bit more trustworthy that there is some different, more complex shape. But if we see the contours, we again find out that this is just a fake. And therefore, the displacement mapping is a solution which also changes the real position of this of our object. And how is this done? Well, we are performing the texture mapping, and in the texture you will have the displacement. The information of the displacement, so the texture, will contain small little displacements. And then at each position we will have defined that our object should slightly be displaced in one way or the other so that it corresponds to this displacement vector. And what we do then is we perform a higher level tessellation with some subdivision scheme, and then we will end up with much higher amount of vertices, which we will then slightly change through this texture. So this will mean that our surface is changed, the actual geometry is changed based on this texture. However, these days we have something called a tessellation shader in the graphics hardware. So this can actually happen instantaneously in the hardware implementation and can be governed by such a simple representation as the texture. And the texture we can, for example, smooth, and then this roughness will be lower, and we can easily control this roughness from the texture point of view. Believe it or not, but textures can be used very efficiently also for performing shadow calculations. And this can be done in the following way. Imagine that we are placing a camera into our light source, and we are simply performing um, the rendering from the light source position in the same direction as the light rays would be going. And we will be capturing this light propagation where the light has hit our scene on an image. As we can see here, we have an image plane, and in each position of our image, we can see that we are storing the depth information of in our of our intersection. So once we have this information available, we can perform in the second step the real rendering from the camera position. So the camera will be from our position looking at the scene, and we will be putting for each intersection point, we will be evaluating whether or not, so let's say we are seeing this this point or maybe this point on the surface. We are seeing this point on the surface, and we will be evaluating whether our point is in the shadow or not. And what we can then calculate is for a particular uh, pixel in our depth texture, whether our point for which we are calculating whether it is in the shadow or not is whether its depth is higher than the stored depth for that particular pixel or fragment on the depth texture. So once again, we will be calculating a depth texture which will capture from the light point of view which all elements, points on the surface are illuminated. And then once we have this texture, we will be calculating the shadow rays from our positions of the real rendering, and we will be calculating where do these uh, points are intersecting our light viewport, we can say, and then we are evaluating whether these values are more further away in depth or closer, and that will determine whether our object is in shadow or it is actually directly illuminated. Oh, here we have it actually described in a more detail, where we are calculating the depth map value, which is then stored from the light, and then the actual depth of our position on the surface when calculated from the towards the light source. So the next application of our texturing can be used for environment mapping. So we have already heard about the cube maps, and the cube maps previously were used in order to texture an object, to perform as the texture function for an object. We can have a similar cube map approach, but not for texturing an object, but for making an illusion of an environment. So our objects, our scene, will be enclosed in a box, if you like, which will have on each of the sides a texture, and this texture will be then forming the background of our scene, and we can always perform maybe secondary rays calculations, which will be then hitting this textured environment map, or we can perform also shadow rays and calculate whether we are hitting some highly light and or illuminated area within the environment map, like here on this environment map, or we are more in the darker areas. And based on that, we can perform uh, the shading of the surface area, which is then close to these environment map positions. We can see that it is forming this kind of cross. This is because we have unwrapped our box into such a cross, and we can actually store it in one texture like this, although it will be memory-wise a little bit inefficient, but it will be simple that we have just one texture to, to fetch from. So instead of using the cube map for the texturing of our object, we are using it for depicting the environment and also for performing the illumination or reflection of our environment onto our 3D objects, which are centered around around which this environment map is placed. So this here I basically described these two applications already. The environment map could be realized as a sphere as well. It doesn't need to be a cube map. So that is also possible. But cube maps are typically easier to handle, as we have already discussed earlier. Let's come to the final point of our lecture, which is dealing with procedural textures. Now, until now, we have been dealing with texturing, which was at the texture was always somehow pre-calculated and stored in an image. We have not been talking too much about the 3D textures, but there in the 3D textures, we would be also storing the values in the entire 3D volume, and then we'll be just performing the sculpting of our object inside. And we will then be associating the particular texture coordinates, which will be the 3D texture coordinates in this case. Now, completely different approach is to not to store the individual texels, 2D or 3D, in an image, but to calculate it instead. So for example, here you have a small code which will be performing such stripe texture based on the UV parametrization. So we can see that we have some, or based on some point position. What we can see here is we have a point on in the 3D scene, and we would have here some value W, which will be encoding the width of our stripe. And we will be taking the x coordinate values of our point P, and that will be our parameter, into a function, a procedure, which will generate us the coloring. So here we have a sine function, for example, and it defines us that if the sine function with this argument, here is a pi, will be evaluated as bigger than 0, then we will have one color. Let's say we will have the black color. Otherwise, we will have the other color, which will be the white color. And with varying W, we can have either more dense, we are basically changing the frequency of this procedural texture. If we will have an information on the level of the sine function, we can create also a procedural texture which will be not so, which will be much more smooth. So here the sine value is directly encoded, while in this case it is just the sine of the sine function, which is encoded either black or white texture stripe. Sometimes we prefer some structured textures, as we have seen on the example of stripes, but sometimes we would like to use textures which are somehow noisy and resemble similarity to some natural objects, like for example stones, landscapes, etc. Here, often in computer graphics, smart versions of noise functions have been used. The most standard white noise, which we see in this image, is unusable because it just generates us a random pattern of white and black pixels, and we will not be able to use it. If we would like to, for example, model some landscape, some terrain, we would like to see some mountains, maybe some valleys, and so on. And this noise function should be the basis for generating such a geometry. However, the white noise would not be a good idea to use. But sometimes we can try to use a low resolution of the white noise and resample it onto a higher resolution grid in 2 dimensions or space in 3 dimensions in order to create some more continuity in the noise function. However, this still is not very satisfactory, especially because it generates a very low frequency pattern which might be undesired. Therefore, Ken Perlin, back in the 80s, has developed a new form of noise, which is nowadays called as a Perlin noise, and has the following advantage. It is continuous within its neighborhood, so unlike the white noise, where this is not the case, the position has in the Perlin noise function in its neighborhood is of similar value. It's not randomly changing. And or it is randomly changing, but is similar to the value which we have at our current position. And the other aspect which it targets is that it has a high frequency component, which is not present in this resampled low resolution white noise example. How does a Perlin noise work? So Perlin noise function is somehow a combination of various steps in order to generate images of this appearance approximately. These images have a continuity across their values. However, they are still random. So I will explain a 2-dimensional case of a Perlin noise. Although there are several versions of Perlin noise, this could be seen as one of them. This is a 2-dimensional version. However, we would often use Perlin noise in 3 dimensions, where the x, y, and z would be the values in the world coordinates. So what we are performing here is that between the floor of our x and ceiling of our x coordinate, and the same for the y coordinate. So within a small rectangle in 2 dimensions of between the integer values within our scene, we are performing certain function or a sum of a certain function. So there will be 4 components here. And you can see here that we are subtracting the value of our real world coordinate with these integer values. Here is a mistake, here should be a j. And what is this function omega doing? This function omega is performing first within our coordinates, which will now go between -1 and 1. We have first some small omega function, which is a 1-dimensional function here, or now it's a product of 2 dimensions, if there is a product. And this omega function is a simple interpolation function, which is a cubic within the range 0, 1. So if we have a look at this function, which is plotted here, we see the cubic, which is behaving nicely smooth between 0 and 1, is interpolating. So we have here some kind of a so-called easing curve. So I'm exaggerating it a little bit, instead of a linear interpolation, which would result in a less smooth pattern. So we have here a two-dimensional Hermite interpolation, as it is called, first term. And the second term is the way how we generate noise here. The noise is generated as a dot product between our UV coordinates and some function g, which is this function is basically for each of our, so if our high resolution, we will have here, I forgot to say, still some kind of a high resolution grid lattice. It will be of higher resolution pattern than I have plotted, and this representation which is shown here is basically showing us one of such rectangles. And on each position of these rectangles, we are defining some unit length vector which goes in random direction. In 2 dimensions, it goes is a 2-dimensional vector. In 3 dimensions, it will be a 3-dimensional unit vector. And we are performing a dot product with this random vector, with each of these contributing surrounding integer positions. So this is how we are creating our noise function through this dot product here. And we are weighting it with this Hermite interpolation instead of a bilinear interpolation. And that's all. This is the principle of Perlin noise. And with this Perlin noise, you can generate images similar to this one. However, this noise function will result in a noise which goes between -1 and 1. And it could be up to you how you deal with this noise. Either you can simply make an absolute value of it to get it to the range of 0 to 1, and through that you will generate some kind of discontinuity which might be desired for your procedural texturing purposes. Or you might simply scale it and translate the values so that it fits into the range 0 and 1. So this is the way how a famous noise procedural function can be generated. I explained it to you on 2D, but often it will be used for solid texturing in 3 dimensions. And that's all for today. We have been today covering the topic of texturing, how to perform the texturing, how to compute the texture coordinate functions, how to use textures for other purposes just than to conveying or distributing various colors on our objects. And we have learned something about procedural generation of textures so that the content which we generate has an appealing natural appearance. Thank you very much for your attention, and see you in the next lecture.